right? Like, so one's doing something, one's not. So there's where your landslide is.
Still? Is it on? Oh yeah, it's on. To keep us on schedule, we need to get started right now. So first speaker is Dr. Mike Burchell. And I'll let him take it away as soon as his slides get up. He's going to talk about the ammonium pre-treatment.
Yeah. All right. Okay, great. Anybody who's talked to me for probably more than 5 minutes knows that I'm a huge proponent of constructed wetlands for wastewater treatment. You might be tired of me talking about this, but this is something I'm pretty passionate about. And today I want to share with you the importance of pre-treatment of wastewater and maintenance of these constructed wetlands to really maximize the nitrogen treatment potential that they have. This work is part of who's now Dr. Brock Camrath's dissertation. He's now currently an EPA postdoc. And this work was funded by WRRI. And as far as I was able to see, it was the first constructed wetland research project completed at a treatment facility since like the early 1990s. And so it was something that I believe was long overdue. And we also got funding for some of the maintenance that I'm going to show you here at a wastewater treatment plant. Constructed wetland was funded by a CCRG grant by Sea Grant. So surface flow constructed wetlands, which are wetlands that are most similar to emergent macrophyte wetlands, are a great example of ecological engineering because these systems use natural energy inputs, low fossil fuels to actually provide water quality ecosystem services to us, and generally low maintenance, but not no maintenance, okay? And that's going to be an important takeaway today. The potential for nitrogen removal in these systems is well documented. We know that constructed wetlands can remove nitrogen and do so, particularly if the wastewater is pre-treated to a certain level before the water goes into the wetlands. And the reason is because it has high plant and microbial activity, a lot of carbon that's in there, and combinations of aerobic and anaerobic zones that promotes nitrogen removal via plant uptake, some nitrification, and mostly denitrification is our target because most of these areas within wetlands are anaerobic. Despite the success that constructed wetlands have in treating wastewater, there's not a lot of examples in North Carolina, and I want to find out why. There's only a handful of these that are taking wastewater and treating them to a tertiary level across the state. And so we found one of these sites. It's up in Walnut Cove, which is in Stokes County. And we really wanted to use this to kind of demonstrate the effectiveness of these constructed wetlands at this site with the hope that we could help other rural towns in North Carolina that are looking to expand their wastewater treatment or need to fix their wastewater treatment to meet their wastewater permits or even, heaven forbid, exceed their wastewater treatment permits. So this constructed wetland was added on to some lagoon systems. Let's see if I'm smart enough to do this without messing anything up here. Let me give you the laser pointer. Can I see that? Yeah. So primary treatment of the wastewater was through lagoon systems, made its way through a duckweed raceway, which presumably was put in place to allow the duckweed to assimilate nitrogen, and then the duckweed would be collected to remove the nitrogen. I don't think they ever did that. This is a BC Wolverton design, and so he was big into the plant-based ecosystems. After the water left the duckweed raceway, it split into two constructed wetland cells. So the population, about 1,800 people, wastewater goes to this. It's rated for about 500,000 gallons per day, but usually operated about 150 to 250,000 gallons per day. The two wetland cells combined are about 3.3 acres total. Split that in half for each cell. The design depth is about 1 foot. It's a TIFA dominated constructed wetland with a design hydraulic retention time of about 5.5 days. And the permit limits for BOD and TSS are 30 milligrams per liter. But ammonium was our real focus here, and it's permitted for 10 milligrams per liter. So the idea, if you look at the sizes of the ammonium balloon, the nitrate balloon, and total inorganic nitrogen balloon, this kind of shows you what the design strategy originally was here. That the wastewater will come in is mostly ammonium, be nitrified through aerobic processes in the lagoon and through the duckweed raceway, reducing the amount of ammonium, increasing the amount of nitrate until it gets to the constructed wetlands, and then denitrification processes with a little bit of nitrification processes would take over in the constructed wetland to result in a wastewater effluent that would be low in ammonium and low in nitrate. So we started monitoring this with high hopes of being able to show how well this wetland was working. It was initialized in 2016. We started continuous monitoring of the inlet and outlet flow and water quality. It was a great setup for monitoring. You know, you had 2 cells there, so you had replication. The infrastructure was already in place there where you could monitor the inlets and the outlets as the flow came in through some rectangular weirs. So we're able to set up ISCO automatic samplers to help measure flow and collect continuous water quality through there. And we set up an online weather station there to help for our water balance. So we started looking at some of the MPDES effluent data at Walnut Cove. And incidentally, one of the problems with constructed wetlands in North Carolina is that they don't have any inlet information. So you only get this outlet information. So you really don't have a good feel of how well the treatment wetlands actually look working. But when we were looking at the ammonium trends in the last 10 years, we noticed this kind of startling trend of ammonium going up at the effluent from this wetland. And we weren't noticing any noticeable changes in flow. So that started, we started scratching our heads about that. And then when we started collecting samples, we started noticing that there wasn't much nitrate coming into the wetland, and the ammonium that was concentrations that were coming into the wetland were essentially unchanged going through the wetland. Red flag, not good. So essentially you could argue that for nitrogen treatment, these wetlands really weren't doing anything, which was a huge surprise to me. But when we started digging into it, it actually kind of made sense. When I started looking at this system and looking at some of the other systems across North Carolina, we were noticing that there was 2 major issues that seemed to plague these systems. There was a detrital mat that was building up within these wetlands at about 1/2 to 1 inch per year of just the growing and dying cattails through a year. What this was causing was poor mixing, short circuiting, reduced retention time, and oh no, all that nitrogen that was in those plants after they died was potentially becoming a source. And then, of course, the lack of pre-treatment or nitrification to convert the ammonium to the form that we really wanted to treat in nitrate because of limited aeration upstream. And so if no nitrate enters, nitrogen removal cannot occur through denitrification in this mostly anaerobic wetland. And, you know, to some of the operators' credit, it's kind of difficult to see, you know, whether you can see these, you can't really see the detritus building up necessarily. And so when you start draining these, you can see these preferential flow paths. And then the detrital buildup can create a strong ammonium diffusion gradient in the water column. And the higher, you know, the lower the ammonium in the water column, the higher the contribution of the ammonium to the water column. from the soil. And so you've got this internal source. So what was happening is basically no significant nitrogen treatment from the duckweed raceway into through the constructed wetland. So it's really hard to promote a constructed wetlands technology when the local examples are performing poorly. So what can we do? So we started with, let's clean them out. So we wanted to take wetlands that have a low hydraulic retention time with a high internal source of ammonium to one that has a longer hydraulic retention time with a lower internal source of ammonium. So we got a grant from the North Carolina Sea Grant Community Collaborative Research Grant. We took one of the cells offline. We designed a process where we would get an excavator boom to work from downstream to upstream, digging the detritus out as we go, pulling it to the banks, allowing it to dewater and stabilize, leave a little bit of the detritus in the cell because the carbon in there and the microbes, we wanted to leave a little bit of that in there for to remain, to have some treatment. One of the coolest things I think we did is that instead of replanting these with greenhouse plants, we simply grabbed the clumps of cattails as we went and replanted them as they go in like 4-foot sections on 4-foot centers. And it only took about 5 days to do it. And so you can see the kind of the before from the inlet and the out and the after. You can see those big clumps of cattails that we planted there. An aerial view of wetland cell 1, where the detritus removed compared to wetland cell 2, you can see that the vegetation in one growing season came back. Cattail's tough. Everybody knows that. You can just dig it up and just throw it back in there and it starts growing pretty well. And you can see an aerial photograph here of how well the vegetation reestablishment occurred there compared to some of that open water area in cell 2 where no cattails were growing because, you know, there was 18 inches of detritus in there and it was kind of, they were drowning in there. So once we took the detritus out, we called that the wetland rejuvenation, okay? What did the hydraulics look like? Well, we did a bunch of tracer studies and with rhodamine dye, and this was a lot more complicated than it looks here to come up with some of these this data. But bottom line is that we increased the hydraulic retention time in the cell that we cleaned out to about 3 days versus the one that we didn't clean out to about 1 day. You know, continued to have about 1 day. So we tripled our hydraulic retention time. And then when we started looking at the concentrations of ammonium in there, we saw finally some decreases in ammonium concentrations in the cell 1 that we cleaned out, and still an increase in ammonium in the secondary cell. Okay, so it was kind of nice. We had a control to compare what our maintenance there. And essentially we had about a 27% decrease in concentration of ammonium in the cleaned out cell versus an increase of about 17% in concentration in the one that was not cleaned out. What does this mean for load? It means that about a 15% load was removed in cell 1 compared to about pretty much flat, no nitrogen treatment in the other cell. Okay, so not going to win any awards on 15% nitrogen removal. Okay, so I'm not going to be bragging too much about this, but we did show that ammonium treatment improved. But I said before, wetlands are not great nitrifiers. They're better denitrifiers. So what would happen if we actually had nitrate going into this area? So we weren't generating a lot of nitrate. And so we actually did a nitrate dosing study where we dosed the wastewater with nitrate using calcium nitrate, and ran a 5-week nitrate study, this dosing study through March, April of 21 to simulate pre-treatment. And it was pretty warm there. And so we were able to come up with some reasonable results in nitrate removal. As you can see here, the influent nitrate, you can see the concentrations that are up between 5 and 10 milligrams per liter most of the time. And then the nitrate concentrations coming out of cell 1 that was rejuvenated versus the control. The rejuvenated one and the control were kind of neck and neck with slight improvement that we can see there in cell 1. And then the same trends of ammonium. A little bit of treatment in the rejuvenated cell, not so much treatment in the cell that we did not treat or did not remove detritus. So we saw about an 82% reduction in nitrate in the rejuvenated cell, and surprisingly, a 74% reduction of nitrate in the cell that we did not clean the detritus out of. Presumably because the conditions were still really good for denitrification within that cell, even at a 1-day retention time. And still the same trends with a little bit of treatment in the cell 1 from ammonium and not so much in cell 2. So we did some scenarios. What would happen to overall nitrogen treatment if we were to convert 25% of that ammonium to nitrate upstream, or 75% of that ammonium to nitrate upstream? And what you can see is that it would result, a 25% change in ammonium would be an overall, because of the denitrification that we would have in a rejuvenated cell, we would increase our total nitrogen removal from 18% to 30%. And then if we could convert as much as 75% to nitrate before it entered the wetland, have great denitrification, we could get that total nitrogen removal up to 55%. And it's not a big change. We just have to get more of that nitrate coming into the system. So key takeaways here: constructed wetlands, excellent nitrogen treatment systems, but the magic wears off without maintenance, and if you don't give it what it treats best, nitrate. So you got to maintain your wetland. It's not that expensive to do the detritus removal and give them nitrate. And we're trying to share some of this experience with those that are operating these wetlands and those that are thinking about using constructed wetlands for adding on to rural wastewater treatment systems. I think this is actually a success story, because after we cleaned out the cell, the town was motivated by our results to actually clean out the other cell on their own dime. And so I think anytime you can get that to happen, that's the type of outreach and collaboration you need to do. And hopefully other towns start looking at this as well as a success. Last slide. My future vision for constructed wetlands in North Carolina is, if I had all the money in the world, I would put half-acre wetlands downstream of every package plant in North Carolina that treat ammonium to nitrate, but discharge nitrate into our streams. There's plenty of unaccounted for nitrate that comes out of these package plants, and most half-acre wetlands at most of these sites could reduce that amount of nitrate by 50%. And I think that would go a long way if we could do that at 400 of these package plants that are across North Carolina. It's a big goal. Maybe there's some nutrient crediting that we can do to facilitate that, but that's what we're looking for the future. So thank you.
I'm sorry we don't have time for questions, but if people want to ask questions, we can hang around after the end of the session. I need to introduce Dr. Charles Humphrey now. He's going to talk about long-term evaluation of permeable reactive barriers to reduce groundwater transport of nitrate from on-site wastewater systems.
Okay, good morning, everyone. So just to let you know what you're in for over the next 15 minutes, I'm going to give a brief outline or overview of nitrogen and public and environmental health, discuss on-site wastewater systems or septic systems and how they process nitrogen, how we can remediate nitrogen in groundwater, a specific case study that I'll go into more detail on and is sort of the focus of the talk, and then summarize that data. So nitrogen is an essential nutrient for plants, animals, humans. It often limits primary productivity in the terrestrial and the aquatic system. So as soon as we add that to land or water, we stimulate growth. That's good in some instances. As the global population increases, we need to grow more food. As the population increases, there needs to be more housing, which covers up farmland. So we're really squeezed to try to get as much as we can out of the existing farmland that we have. As the population increases, so too does the generation of wastewater. Wastewater treated by septic systems, sewer plants, et cetera. But it's enriched with nitrogen, that waste. It's important that our wastewater treatment systems, our ag production, we try to reduce how much nitrogen gets into our waterways. When it gets into waterways, it can cause algal blooms, again, stimulating growth. Some of the algal blooms can produce toxins, which are dangerous to humans and animals. That can lead to fish kills, water use impairment. And we've kind of seen that over the last several decades in North Carolina, the US, and really across the world. Specific to nitrogen, if we have elevated nitrate concentrations in water supplies, that can be deadly to infants through methemoglobinemia. And also there's been some studies showing that even below 10 parts per million nitrate, that if you chronically consume water that has high nitrate concentrations, that can lead to some cancers. So again, the point is nitrogen is a very important element. We have to add it to our fields to stimulate crop growth. We sort of digest and transmit that through our waste. We have to treat the waste properly to make sure that the nitrogen or too much nitrogen doesn't get into the waterways. What I'm going to be discussing are on-site wastewater systems and how they treat nitrogen and in some cases don't treat nitrogen. So again, on-site wastewater systems or septic systems have about 4 basic components. You have the septic tank, the drain field trenches, the soil beneath the trenches, and then I also like to include landscape processes. So we have setback distances from the system to things like, creeks, monitoring wells or water supply wells, property lines, et cetera. The nitrogen that's processed by septic systems, most of it comes into the tank as organic nitrogen and ammonium. And within the septic tank, we have ammonification, which microbes convert the organic nitrogen to ammonium. So what leaves the tank is typically 75+% ammonium. If the ammonium is sent to drain field trenches that are in well aerated soil, so groundwater is well below those trenches, 45 centimeters or so below the trenches, that typically is an environment where that ammonium gets converted to nitrate through the nitrification process. Both ammonium and nitrate are plant available forms. So if we have roots of plants, trees, whatever, extending into the drain field trenches, they can uptake that nitrogen and convert it to organic nitrogen. So that's a removal pathway. In many cases, what we see is that these systems that are, again, installed properly in the correct settings are very efficient at converting ammonium to nitrate, that nitrification process. But the nitrate gets leached into the groundwater because there's not really a carbon source between the drain field trenches and the groundwater table. Most of the carbon in the soils, like in the A horizon, the topsoil, and even though there's a lot of carbon in wastewater, it gets oxidized in the soil as well. So that's kind of what we're missing. And so in many studies, and I'll provide some examples of those, we see a lot of nitrate that gets leached to groundwater. And this can create long plumes of enrichment, groundwater enriched with nitrate that can extend for 30, 40 plus meters. Ideally, what we'd like to have happen is that once that conversion of ammonium to nitrate occurs immediately beneath the drain field trenches, we would like to have some organic matter in the soil right beneath those trenches such that when that nitrate leaches through towards the groundwater is saturating the soil. We have the carbon source there, right? We can get denitrification right below those trenches, and that prevents groundwater from becoming elevated with nitrate. It also prevents, these nitrate plumes from forming. But again, in many cases, that's not what we have in these settings. So there have been a number of studies conducted in Canada, the US for 30, 40 plus years, where they've documented this. They've seen where the systems were very effective at nitrifying wastewater, right, in the soil right beneath the drain field trenches. And you can see plumes of nitrate greater than 30 milligrams per liter, right? That's 3 times the drinking water standard that extend 20 plus meters away from the system. And, if we think about our rules in North Carolina, our setback distances are typically 15 to 30 meters. So again, there's some environments where we can have these groundwater impacted by septic systems. There's another study by Harmon. They looked at a school system, which has a higher strength wastewater. 50 meters downgraded from that system, it was still 30 plus milligrams per liter. Closer to home in Virginia, there was a study done in the early 2000s where they looked at 3 septic systems and saw groundwater nitrate concentrations exceed 10 parts per million. And then the researchers at East Carolina University, some of my colleagues and myself, we've worked on some studies where we've evaluated this. We have installed monitoring wells adjacent to drain field trenches, down gradient from systems to see, you know, what was in the tank, what's in the groundwater next to the system, and then what's moving and what are the species that are moving along that flow path. So some of the things that we found were that when groundwater is close to the drain field trenches, we don't have nitrification. We have discharge of ammonium and organic nitrogen to groundwater. And in these sandy environments, that also is mobile. So it's not just nitrate that can move through the aquifer system, it's these other forms as well. Climatic conditions can influence like the numbers that we get in the groundwater beneath the systems during very dry periods where there's not much rain and dilution. The only recharge may be from, you know, these septic systems. And so it kind of gets concentrated beneath there and the numbers go up. And the groundwater, if it's enriched with nitrogen, again, is connected to adjacent surface waters. And so that can be a flow path and a source of nitrogen that influence not just groundwater, but also surface water. Now, there's also been some studies which have shown in the hyporheic zone, or also if there are riparian buffers between the systems and a creek, that there are some natural processes that occur that really help prevent nitrate from discharging into surface waters. So it's very possible that we can have high nitrating groundwater near systems, but it may not actually reach surface waters because of what's in between those two. So if there are, again, riparian buffers or organic rich soils, hydric soils, that groundwater is upwelling and moving through to get to a creek, you can get 75+% removal of nitrate before it ever reaches, again, the surface water. So again, these are some of the scenarios that we've seen and other researchers have seen. There are processes that can be available to help prevent surface water contamination from septic systems, but not all locations have riparian buffers. They don't all have hydric soils between the systems and a point of interest. The point of interest may be a groundwater supply well, right? It may be a property line. So in those scenarios, what can we do to help these systems out, again, in terms of removing that nitrate? And so there have been some studies done on what are called permeable reactive barriers or denitrification trenches or denitrification walls. There's a lot of different terms for them. I kind of picked the permeable reactive barriers. I thought that sounded, you know, sciencey. So I was like, all right, that sounds good. Let's go with that one. But they're really all the same thing, right? It's kind of like you're creating the conditions that you have in a riparian buffer in a place where there's not a buffer. So the idea is if we know where groundwater is impacted by the septic systems, the nitrate plumes, we know the depth, we know the width through groundwater monitoring. Why not put what's required at that depth so that when groundwater with that nitrate moves through it, it's kind of simulating what would happen in like a riparian buffer. So we're providing the carbon source there for the microbes to convert nitrate to N2 gas. So again, these have been used for 30+ years. There was one of the earlier studies that was done. They looked at 14 years worth of data for one of these permeable reactive barriers that was installed to treat drainage from a dairy. So really high strength wastewater. After 14 years, they said it was still 92% effective. It reduced nitrate transport by 92%. They took some samples of the carbon that was in that barrier. They did some tests on that and said it should last about 66 years. So again, based on those studies. So that certainly tells us these can be long-term effective practices, relatively low maintenance and passive, right? One little more recently, or with longer term data, was a study by Robertson and others in 2008. And this was a study where they had 15 years worth of information on a groundwater reactive barrier. They said after 15 years, the efficiency of that barrier decreased some, but it was still very effective at lowering the concentrations. The denitrification rates were influenced by things like temperature and available carbon, and sort of the size of the carbon material that you put in there influences its duration. So things that are sort of finer texture burn off quicker, larger, coarser material may last longer. So it's probably good to have a mix if you're going to install something like that to, again, looking at the short term and the long term. Okay, so specific to what I'm talking today is sort of the background information. I guess about 7-8 years ago, I was called by the state of North Carolina, DHHS, and they had a school site that was being monitored. They installed a septic system back in the early 2000s. They had 3 monitoring wells labeled 1, 2, and 3 that they installed around the new drain field. And they were required by the state to collect water samples from those 3 wells 3 times a year. And the first couple of years, it was fine, right? So the concentrations of nitrate in all wells was below 10 parts per million. After about the third year, what's shown as well 2, the red line, it started to spike up. And after about the fourth year, every sample was higher than 10 parts per million, 10 milligrams per liter. And so at this site, well, they knew the well depth, they knew the screen depth, they had information about which location was being influenced. What they weren't sure of is it actually the school that's the source of that nitrate? Just to the south of that school, there was a church that was built. It had a septic system. And then there was a little bit of finger pointing, like, whose fault is it? We've had this system for the school in place for a couple of years. The nitrate numbers were fine. Now they're higher after the church built their septic system. So with the 3 wells, we did a 3-point problem calculation, 3-point contouring. Unfortunately for the school, flow was to the northwest. It was their fault, right? So they wanted to again address this. So with a little bit of money from DHHS, we're like, all right, well, let's try one of these barriers, right? There's this prior research that shows they can be effective. We have information on how deep this plume is. We know where we need to target it. So with a little bit of money from the state, we're able to put in a trench, a denitrification wall, permeable reactive barrier between that well 2 and the septic drain field, which is outlined in the red there, right? So right between the 2. And the idea is, again, that groundwater enriched with nitrate moves through that carbon source. And then as it moves through there, microbes convert that nitrate to N2 gas. But we have to add the carbon to it. This site was maybe not typical for Eastern North Carolina. It was pretty deep to groundwater, a little more than 18 feet. So we had to have an excavator with a pretty long arm to dig down that far. Luckily, the school was doing some work out there anyways. They had contractors, so they had some of this equipment that kind of reduced some of the costs. But we put in a trench. It was about a meter, a little over a meter wide, 8 meters deep, about 6 meters long. And that's an estimate because when you start digging, things start sloughing off a little bit. It's not exact. But we did that again right downslope or upslope, if you will, from that well too. And these are just some pictures showing like the installation process. So again, the wood chips that we got were actually donated from a local paper mill. And then the school had dump trucks, so they picked it up and they brought it to the site. They kind of overdid it with the wood chips. I mean, there's a lot of carbon in there, but we put it all in there and we covered it up. And again, they had to continue monitoring this site just like they did the previous years. 3 times a year, they collected the samples. So once the barrier was installed, we tested for other things, right? So the state requires them to look for nitrate, fecal coliform, and some other things. They don't look at ammonia, they don't look at TDN, they don't look at DOC, but we wanted that information so we could see if this barrier is actually providing the carbon to fuel denitrification. And then we also looked at things like pH, DO, oxidation reduction potential, et cetera. And these are some pictures of the school personnel. They were sampling the wells and they were giving us access to the pump tank to get wastewater samples. So again, we only had a limited amount of money and sort of end of the year money that DHHS had. And we could only sample about 5 or 6 times prior to the end of, the project. And so this is some of that data for like the first few weeks after that barrier was installed. And just to kind of summarize that, the nitrate concentrations in that well 2 did decline even over that 6-week period. We saw an increase in dissolved organic carbon, which we kind of expected because we put a carbon source down there. The chloride concentration slightly increased, and we're looking at chloride as kind of like an indicator of the wastewater, right? So if we somehow put that barrier in, or the reactive barrier, and it's less hydraulically conductive than the soil around it, groundwater may be diverted away from it. And then we'll see a drop in chloride because wastewater has a higher chloride concentration than natural groundwater. But if the chloride concentration stayed steady or increased, we know that, hey, that's the wastewater signature. We didn't just divert water around it, it's actually moving through it. So the chloride concentration slightly increased, that was good. Oxidation reduction potential was in the range that you would expect denitrification to occur. Fast forward to today, since 2016, the mean yearly nitrate concentrations for well 2 have all been below 10 milligrams per liter. So for the last 5-6 years, they dropped. You can kind of see the picture on the top there where the barrier was installed. I mean, there's a pretty quick drawdown. 17 of the 18 samples, again, that they have to collect, over the years from well 2 have been below 10. So it's doing its job. And if we compare pre-barrier to post-barrier, just all the information, we see about a 32% overall reduction, but certainly it's below the threshold. And we can plot that right before and after. There's a good regression. Groundwater nitrate concentrations were increasing by about 2 milligrams per liter each year after the monitoring started. After we put in the barrier, they dropped about 1.4 milligrams per liter per year, and that there's a good relationship there also. So again, just to kind of summarize, we've got elevated nitrate loadings to surface waters continues to be a problem at all scales, global, national, state, local. Prior research has shown that riparian buffers, reactive barriers can reduce the delivery of nitrogen from terrestrial to aquatic systems. So research supports that. The 7+ years of field data after installation of the barrier at this school seems to show that it's effective as well and continues to be. I would like to see more work to assess the treatment performance and economic viability of these barriers as retrofit practices, and also for installation of new systems. So there's been some other research where we can kind of create the media beneath the trenches, especially in sandy soils, to help stimulate some of these processes. And I think there's enough information out there where we should be able to move forward and try to test some of this stuff out, so we see more of these practices put in place. All right, these are some of the references listed. Certainly would like to acknowledge all the cooperators that have worked on this project. And with that, I'll take questions.
Please, if you have any questions, you can come up and use the microphone in the front. We do have a couple of minutes, so. I'll start with one from the chat. Oh, it just disappeared on me. This is from Alex Manda. What is your estimate of costs for the reactive barrier if someone were to pay for all activities?
Well, let's see. Adjusting for inflation from 7 years ago. Well, no, that's a little difficult to. Essentially, I can tell you what we paid for that one, but that's not the full cost. We had about $3,500 total. That's including monitoring and everything to put this in. Some of the costs were reduced because the contractors were already on site, so they didn't have to pay for mobilization. The school provided the dump trucks. They provided the loaders to load the wood chips. The wood chips were donated. So this particular one, I mean, if you had to price all of that out, probably somewhere between 10 and 12,000, something like that. That would be my best estimate. So.
We have time for one more question.
What do you have a situation where you have like a roller coaster plane or one of the islands where you water is way up there and they actually shouldn't be put in septic systems? Do these which are very, they be effective in such a situation?
Well, the key, like Dr. Burchell was saying, is you have to have nitrate coming into them. So what we've seen is that if groundwater is really close to the drain field trenches, you just don't get that much conversion. It stays in ammonium organic. So it probably wouldn't be effective there. There are other media that possibly could be used in that situation, maybe to sorb ammonium, but but then you have also the other pollutants that you're concerned with, that's not going to address, the pathogens and so forth. So I would say like these can be, based on our work and then other studies, these certainly can be cost-effective, low maintenance retrofits where you have systems that are nitrifying the wastewater,
Great. Thanks, Charlie.
Thanks.
Next, we have Holly Miller. She's going to talk about decentralized wastewater management.
Well, I'm not going to take too long here. I know we got lunch coming up after this, so thank you, Nathan, for the very shortened version of that long title that we all put. So I am with Tetra Tech. I'm an engineer, so I'm not a scientist. So forgive me if I say anything wrong or say nitrate instead of nitrite, that kind of thing. But we were hired by the town of Nags to update their decentralized wastewater management plan. And I want to thank the town of Nags head project manager, Kylie Shepard and Holly White, as well as the Decentralized Wastewater Management Plan Advisory Committee. We worked for a whole year on updating this plan. And also ECU, Charlie and Mike O'Driscoll did some groundwater monitoring for us as well. So just to give you a little bit of background on the Decentralized Wastewater Management Plan, we were tasked to update the plan and look at from the original plan that was developed in 2005 and figure out what that looks like today. So just to kind of back up a little bit, the town started a septic health initiative back in 1999. And what that was to promote proactive maintenance of these septic systems. A lot of times folks moving into coastal regions don't know what a septic system even is. They're not used to that. They don't know that they need to pump it out every 3 to 5 years and what that really means for our ecosystems. So the town invested in having free inspections to these homeowners to make sure that they knew what to do. They knew their system might need to be pumped out. And they also gave out rebates in water utility bill credit to homeowners. If they actually did get it pumped out, they would turn in a receipt and get it in a small credit. And they also had low interest loans. So if you had a failing septic system, they provided a low interest loan to be able to repair that system in a coastal environment. And then what I'm going to be talking about today specifically is water quality sampling. So the town understood that there were some treatment issues, as Charlie mentioned, with groundwater tables rising and all of these different issues in a coastal environment. You're not getting all of the nitrate and effluent treatment in septic systems. So they understood that there needed to sample some water quality to see if there were hot spots, to see if there were failures. Because septic is underground, until it bubbles to the surface, you don't really know there's a failure or it backs up into your house. And hopefully none of you have ever faced that situation, but it's a messy endeavor. And at that point, the system has failed and you have to replace the whole entire thing. So in 2005, as I mentioned, the town developed a decentralized wastewater management plan. We updated that, and I'm going to talk about the data analysis here today. So just a quick update on what the Decentralized Wastewater Management Plan included was stakeholder and community input, a new vision, mission, and goals, a connection to other plans. Because septic isn't a standalone program, we also looked at stormwater, flooding, and really risk to the area. When hurricanes come in, when it floods an area, that actually affects septic too. And people sometimes don't not make that connection necessarily. In addition, the Septic Health Initiative program, we reviewed all the data, all of the inspections that were conducted, all of the additions and recommendations within that program. And then a new piece of that was the groundwater that I'm going to talk about today as well. And we looked at future conditions. As Michelle mentioned earlier in our opening session, what does that look like? What does climate change look like for septic? And can we mitigate that? Is that going to be a problem in the future, especially as we see sea level rise and groundwater changes happening? And then obviously, there's lots of funding opportunities that are out there now too. And then can that be used for septic systems? So we included that all in the new plan and the update. So for water quality and bacteria, really want to dive into what that looks like. The town collects water quality and bacteria samples for over 23 sites. I'm going to show you a map here in just a minute. And they collect it monthly in surface water locations, as well as in stormwater and groundwater. So they've got a gamut of multiple different sampling locations throughout the entire town. There's over 2,000 data samples in a large span from 2011 to 2020. Now the data has never been analyzed. So they were just collecting data, dumping it into an Excel file, but not really doing anything with it, not really analyzing the data, figuring out, oh, there's a high spot here, there's a, this area is good. What does that really look like? So in this update, we analyzed all that data for them. And let me tell you, just compiling the data alone was daunting, not even looking at the data, doing statistical analysis on it, figuring where those hotspots were. So collecting all that data from the town, moving forward, they have a really great system in place to make sure that that is not going to be an issue later. And here we have sample parameters that were collected from the town, including nitrogen, ammonia, nitrate, and nitrite, total phosphorus, also fecal enterococci, and E. coli. So they're collecting 3 different bacteria parameters. Maybe a little bit of an overkill, but they had several different varieties of bacteria that they were collecting as well. And here's a map of all of those locations. So in Nags, that is very linear. They are collecting from the northern end of town at 8th Street all the way through Cape Hatteras National Seashore, and we call it South Nags Head. So there's a very large group of data that they're collecting every single month, and it's a lot, right? But you can see that there is a gap between the bypass by Whalebone and Junco's Ditch. So there's an area that is not being sampled currently, and we actually made a recommendation to add additional sampling locations in that area so you have a better spread of what that looks like and see if that area is a problem, because right now we don't know. So let's get into the water quality data itself. As I mentioned, the data was collected for over 10 years, and we had that nitrate exceedance criteria limit was set at 10 milligrams per liter, as Charlie had just mentioned, per the state standard. And we also had the ammonia and total phosphorus exceedance was set per EPA standard. So those were kind of our levels that we said, okay, if things are below this number, not necessarily a big issue, but if it was above those exceedance limits, we red flagged it. Basically, that meant it could be a potential hotspot for septic failure. And then if we did identify it, then is there something that needs to be done? Is it a system? Can we trace it back to a location? Or is it animal waste, that kind of thing? So it's hard to correlate those two because you don't have that direct connection between them. So the data, looking at all of those 2,000 data sets, we found nitrate exceedances over 10 milliliters were reoccurring at 4 primary locations. Old Cove Well, which is on the sound side of Nags Head, just south of Jockey's Ridge, if you're familiar with Nags Head. The Nags Head Fire Station actually also had high exceedances, which is kind of in the middle of town where all the municipal buildings are. And then the Bypass North, which is just a little bit south of there, kind of close to Whalebone Junction and Jeanette's Pier, if you're familiar with that area. And then Junco's Well, which is on the south Nags Head, kind of towards the end of Nags Head limits. That area had very high exceedances. You can see here the mean was 16.3 milligrams per liter. So definitely changed as you go from north to south. The higher levels were in the southern part of Nags Head. And just a note, ammonia and phosphorus concentrations were pretty even across the board, and we didn't see any high exceedances, so we didn't focus on that parameter nearly as much as the nitrate. So here's a map of those locations. The spots in orange are the high exceedances, as I had mentioned, and I just pulled out the top 4 so you could kind of see what that looked like. And then the plot there too, you can see it visually. This really helped the town of Nags Head understand what that looks like. They're not scientists, they're not engineers, so we had to visually represent it to them to make them get the data, basically, without having all the background in the information. So for bacteria, as I mentioned, they had 3 different bacterias: fecal, enterococci, and E. coli. The fecal coliform was monitored only for a short period of time, from 2011 to 2013. The criteria was at 200 milligrams per, 200 colonies per 100 milliliters. That's the state standard. Enterococci was at sampled at groundwater sites. And it had a good coverage for that duration of the sample period, 2011 to 2020. And then the enterococci exceedance was actually set at 35 colonies per 100 milliliters. And you probably, if you know anything about bacteria, you're like, why is that so low? But because of the recreational nature of Nags Head, that's the beach closure limit. And so we wanted to actually set that limit lower because of the recreational nature of that area. We could have set it at the higher limit, but we were thinking that that limit would actually be very beneficial for the town of Nags Head to try to understand and hit, because so many people are recreating both on the sound side and the ocean side. And then, as I mentioned, E. coli had a small sample data set, but there wasn't enough to really analyze the data. So we actually didn't look at it in great detail. So to dive into the fecal coliform, there were exceedances across all sites. You could only imagine in a beautiful place like Nags Head, what does that mean? And do people who are renting those homes even know that information? No, you're there for vacation. You're there to have fun. You're there to go play on the beach. And so this data, although it was very good, is it useful for the general public? Probably not. So we had to understand how to communicate that to them without scaring people. And sometimes that's really hard because their tourism base is, a huge part of their economy. So in general, the highest fecal coliform exceedances above that 200 colonies per 100 milliliters were at 4 primary locations: Wrightsville 1 and 2, which are in the northern part of town. They had mean concentrations, at 300 and over 500. And then Junco's Ditch and Junco's Well, which are in the southern part of Nags Head, had fairly high concentrations over 500, well over 500 and over 200. So you can kind of see the spread is high. It's not ridiculously high, but it is still very high. So again, we red flagged these areas and needed to sort of start to connect the dots: water quality, bacteria, and then what is that management plan moving forward for these areas as well. And then enterococci, as I mentioned, the 35 colonies per 100 milliliters, there were exceedances at most surface sites, as you could only imagine. And these numbers are a little alarming. You're like, are they off by a decimal? What's actually going on? But the Wrightsville 2 had exceedances nearly at 4,000 colonies. Old Road, which is on the sound side, has over 3,500. Bypass South, mean, was nearly 500. And South Nags Head Ditch, almost 6,000 colonies. And that kind of correlates with all of the other sort of hot spots that we had already identified. And you kind of start to question, are these numbers real? Do we need to go back and sample these numbers? What's actually going on? So you start to question what that looks like. And then you have to think, okay, what is the solution? How do you fix this? Especially with a community like Nags Head, they do not want central sewer. They want to stay on septic. And as we heard earlier, sometimes septic actually has better treatment than a wastewater treatment plant to some degree, because there's no sanitary sewer overflows. Even though there's flooding problems, even though there's groundwater problems, it actually could potentially be better. So we had to think about that in our solutions as well. And as I mentioned, the fecal data is shown here. And you can see the spread it's kind of all over the place. It's sort of hit or miss, left and right. And then the enterococci is alarming. As I mentioned, there's a lot of orange on this map. And so you almost have to take that with a grain of salt to some degree and say, okay, there's a problem. What are we going to do about it now? And so switching gears just a little bit, in addition to all of that, with my 5 minutes remaining, I'm going to dive very quickly into groundwater analysis. So ECU CSI, as well as Mike O'Driscoll and Charlie Humphrey helped actually did all of the groundwater analysis. They looked at 6 locations in Nags Head, as well as multiple other locations in Dare County over a 12-month period. And what it was is to determine if, yes, that nitrogen and enterococci, if that data was true, if that is actually coming from septic, or is it coming from something else? What's going on under the surface? So in general, the separation distance from ground to groundwater, it's required to be about 3.5 feet in a coastal sandy environment. So I just drew a little picture for y'all just so you can visually understand all of those pieces. Oops, sorry. And just another visual, as groundwater rises into the drain field, it's directly mixing and limiting effluent treatment in that area. And then that nitrate is going directly into groundwater and or surface water. And that's probably why we were seeing some of the issues that we're seeing in the sample data, in addition to lack of treatment. And there's just a picture of Nags Head flooding after Hurricane Matthew. So not to compound the issue, but there are obviously flooding issues with rainfall, as well as ocean overwash and hurricanes. This picture was actually taken after Hurricane Matthew. There was about 3 feet of standing water. And when that happens in a septic area, you have direct mixing coming to the surface, and lots of bad stuff that people will kayak through and walk through. And so it becomes a public health issue at that point as well. And here's the sample locations. Again, the spread in Nags Head was from north to south, decent, as well as the other areas within Dare County. And just a quick summary of what that looks like. South Nags Head, Bodie Island, and Wright Brothers Memorial in the north, all were below those requirements. That 3.5 feet that I had just mentioned, they had shallow groundwater tables. Basically, none of those areas met the requirements. And so another red flag goes up. So you've got multiple red flags that are happening, and that helps you figure out the management plan side of things. Other locations Nags had at the municipal building, as well as Dowdy Park, they had a greater than 3.5 feet depth to groundwater, but it was getting closer. And so it's kind of like a medium issue, not there yet, but if groundwater continues to rise, it could be a problem in the future. And then Bonnet Street, beach access on the ocean side, interestingly enough, had deeper groundwater tables. So we started to infer that Oceanside might not have as many challenges with groundwater as Soundside, depending on the mean sea elevation. So the higher mean sea elevation you have, the depth of groundwater is deeper. So you kind of get that correlation between those two. And here's just a visual of what all of that data look like that ECU compiled. You can see there are multiple areas that groundwater is well within the drain field trench, and that obviously is going to lead to a failed septic system, direct effluent mixing with groundwater and or surface water. And interestingly enough, the South Nags Head residential site, this is the data from the residential site there. We've got low mean sea elevation, and groundwater was in the trench pretty much 100% of the time. Definitely a challenge. And here's kind of a projection of what it was when it was built versus now, and in 2050, what that could look like in the future. So I don't think this is the only location in South Nags Head that is a challenge. So additional studies will definitely be needed in that area to determine if that is the case. So just a quick last slide. Long-term data suggests that groundwater is actually rising faster than sea level rise. And Charlie, don't let me take any of your thunder, please. But it's rising at 0.343 inches per year. And that is actually faster than sea level rise. So it's going to be more of a problem than sea level rise in this scenario. They may contribute to additional septic systems that have failures or potential failures. And then those future conditions, we didn't even project future conditions in this area. So that will compound this issue as well. And there's just a visual of what that looks like. And in that addition, I won't get into this because we don't have time, but we also did a risk assessment and what that looks like. All of those hotspots we compounded together, and this will be used for further education, treatment, and targeted potential retrofits of septic and or declustering or clustering systems in areas that will have failure either now or in the future. So with that, these are the next steps. We'll be adding some additional water quality monitoring, as well as looking at additional groundwater loggers to get a better idea of what that data looks like. moving forward. And this is just a very small piece of that plan. So with that, I probably have no time left, but thank you very much. I don't know if we have time for questions, but thank you.
Well, we have time because we're at the end of the session. So
Perfect.
yeah, we don't have anybody afterwards. So yeah, if anybody has any questions, please.
I actually have a student who's really interested in this topic, and he's in Washington, but looking at the Outer Banks. And so I've asked him to look at your work. I was just going to send him a link to the draft plan. Does it have some of this analysis in it? I was trying to listen to you and I wasn't looking at the plan.
It does have definitely some. It's got a lot more of the data. And then
Okay.
At the end of the plan, we'll be providing the town all of the data that we have so they can continue moving forward with it. And you've got 2 ECU folks that did all the groundwater
Yeah.
information right here. So they're definitely great resources as well.
Yeah, and I guess that would be my follow-up question. And he really has to do that research, is like what academic research is there around this topic, specifically with sea level rise and septic or on-site wastewater management?
There's quite a bit, and I
okay.
don't think people they don't make the connection yet, but it is definitely a problem. And I was actually talking to someone up in Virginia, and they were like, "Oh, it was a red flag, oh moment." So it's definitely something we need to be thinking about, and it's not even included in a hazard mitigation plan. And so that's huge. Big changes are coming, I think. Thanks.
Hi, thanks for the interesting talk. Maybe I missed it, but I was curious, you had a lot of locations, throughout the island, and I was wondering, do you see a lot of spatial correlation, between, like, are there hotspots where, several monitoring stations all are exceeding criteria? And then on top of that, do you see that correlation among the groundwater and the surface water sites? Like, are areas that are having groundwater contamination problems also the same areas that are having surface water issues?
Yes, definitely. So this risk map right here kind of puts all of those things together, and I kind of glossed over it really quickly because I was running out of time because I was talking too much. And it might be a little hard to see on here, but it's in the plan. The areas on the sound side, closer to the estuary, definitely having problems, as well as South Nags Head, and primarily on the Cape Hatteras National Seashore side versus ocean side. There was one other location that was very challenging between the highways. Because of the low mean sea elevation, we're seeing problems in that area because there's elevation challenges, then you've got 2 highways that are kind of blocking the water. So there was 3 primary locations that were definitely challenging, and all of those criteria started to align to be red flags together. So definitely an issue, and further studies will definitely be needed to continue that research. Thank you so much.
Yeah. Thanks, everybody. I think it's time to eat lunch.